Hello, hello.
Good morning.
Well, thanks everyone for coming to our session. This talk documents our adventures into researching vulnerabilities into different bikes manufactured by a certain electric motorcycle manufacturer. But which electric motorcycle manufacturer are we talking about? Well, we can't say. For reasons that we'll get into later in this talk, the manufacturer themselves we're not allowed to talk about at this point, so we've changed the names to protect the guilty. So you will see Moto motorcycles throughout this entire talk, and just know that this is a stand-in for the actual company. Now, if you think you can guess who we're talking about, you can't. Can't do it. But if you were able to hypothetically guess who we were talking about, you would actually be able to follow the steps that we're going to talk about in this presentation and reproduce or identify the vulnerabilities still present. Okay. So to begin with, we need to understand why Persephone and myself chose this particular manufacturer to go into. So first, a little background, we need to understand how a lot of modern not motorcycles, just vehicles in general, modern vehicle manufacturers, how they like to push updates. So making your customer come into a dealership every time you've got a firmware update on your new vehicle, that's really expensive, and in today's world of just constant updates on everything all the time, it's just unacceptable. So what if manufacturers instead just push these updates straight to their vehicles? This is a process known as over-the-air updates, or OTA, and this is especially common on modern electric vehicles. Now, unfortunately, our employer, Bureau Veritas, who sponsored this project, they didn't want to buy us a $60,000 electric car for research. Well, what about motorcycles then? Well, there are quite a few electric motorcycle manufacturers doing OTA as well. And that brings us to our target. So here is Moto Motorcycles page talking about their newest vehicles that support this feature. They have the ability to push updates straight over a 4G cellular connection. So what if we manage to find some vulnerabilities in this process? Malicious firmware on vehicles has serious consequences. If an attacker can modify the firmware on a safety critical system, they could potentially injure or even kill someone. So to understand these kinds of safety concerns, we first need to dig into this firmware update process, see if it has any potential vulnerabilities, and if we do find vulnerabilities that would allow someone to upload their own unauthorized firmware, we would need to understand what these systems actually control in order to evaluate their impact. But where would we even start with this? Well, initial research into this company revealed something called the main bike board. And this appears to be responsible for controlling the main functions of these electric bikes. And it's kind of the equivalent of an ECU on a traditional gas-powered motorcycle or car, but quite a bit smarter and handling quite a bit more functionality.
So our first thought was to attack this sort of at the source and go and attack it on the hardware level. We tried to get MBB, main breadboard, from a licensed retailer. This is the official way to get replacement parts if you're a technician or dealer. And we'd know, in this case, exactly what model we got it from. But unfortunately, after a long back and forth with the retailer and by proxy their contact at Moto, we found that they will only sell you parts, at least for these motorcycles, if you have a VIN number, which we don't. Thankfully, they eventually refunded us the $400 that we tried to pay for it. But eBay exists. So when it arrived, we started opening it up. It turns out that it's sort of structured like a Matryoshka doll, in that it has this ABS shell encapsulating a resin-encased brick, which itself is around the actual PCB. So I'd read online at this point that methylene chloride would melt epoxy, and excitedly went to a chemicals retailer and got some methylene chloride and immersed the board in the methylene chloride, and nothing happened. So turns out, after much more research, that the article I'd read had been kind of wrong, or I'd misread it. After researching more, turns out that methylene chloride is pretty good at dissolving epoxies that are cured, which is the most common type of potting resin, but not so good at other resins. Yeah, excuse me. Like polyurethane. Polyurethane, much harder to dissolve, much more annoying. It turns out that you need either methyl ethyl ketone or a specialized mixture, which has been patented. Found the patent. It's 70% by volume dichloromethane, 20% by volume dimethylformamide, and 10% by volume methanol, which turns out is a class 2 carcinogen, class 1 skin irritant, and highly flammable. And also $200 per liter. So I didn't really want to do that, so we put that avenue of ingress on pause for the moment.
Okay, so Moto really went overboard on this potting. Even if we could cleanly remove the polyurethane without damaging the chip, it's possible that there would be even further obstacles, like chip read protections on the actual components that have the firmware in them. So we need some other way to get this firmware. Well, what if we could intercept the firmware instead? That's the whole point of this. Why don't we just grab that firmware? But unfortunately, we don't have a cellular module. You also needed a cellular module to pull the updates into the main bike board. And it turns out intercepting 4G communications is complicated and potentially illegal. But what if there was another way to perform updates on these bikes? So before they started updating their bikes over cellular, Moto actually used an app and a Bluetooth update process to push these updates. In fact, you can still do this process on modern bikes if the cellular update process isn't working. And this is exciting because it means the firmware is now passing through something we can control, a phone. Ideally, we would push a firmware update to a real bike and simply intercept the communication using, say, a rooted phone that's passing all of its network traffic through a interception proxy. But since we didn't have a real bike, why don't we just reverse engineer the app and understand how it's connecting to the firmware update server and see how is it fetching it to stream it into the main bike board. So yeah, like I said, let's just see if we can spoof that request instead rather than having to actually have a real physical bike. So first, we'll just create a virtual Android device and download the latest version of the app on it. So I'm using Aurora Store since it's a non-Google Services virtual device so that we can grab that APK later. But this is a real app being pulled from Google Play servers. So we just need to grab that APK off the virtual device, pull it down to the virtual machine, or to our physical machine for analysis. Like pretty typical, just ADB stuff at this point. But with that, we now have the fun part can begin. So we can open this APK in JADX, which can extract. Oh, I'm moving the wrong microphone. Thank you, I appreciate it. Thanks. Yeah, so we can take this APK, bring it into JADX, and it will extract the DEX files from the APK and decompile it into Java. And the great thing about this process is that the namespaces and symbols from the decompiled code are they're preserved in the actual DEX files. So JADX is able to show us the actual function names that the developers included. And so for those of you who do a lot of reverse engineering, you know that if you actually have the original symbols, that's a huge benefit. So that made this reverse engineering the app itself a lot easier. And thankfully, they weren't doing any sort of additional things to obfuscate those names or strip the original symbols. So we've got it into JADX. We've got the decompiled Java. But where do we begin with? Well, first we need to figure out what kind of URLs we think that it might be trying to pull these updates from. And an obvious one is that there's this FOTA-server.motomotorcycles.com. And again, I'm redacting this URL, but if you knew the real name, you replaced it. This is a real server on the internet. It's not, we're not just making this up. So we know that base URL, but we have no idea how to interact with it. And maybe we need a motorcycle, like a physical motorcycle, in order to be able to get some sort of authentication data to interact with it. So we're still not there yet. So let's just look at what references that constant, what references that firmware update constant. Well, we see this API call for firmware within the APK, so that looks pretty promising. So the actual request is happening right here. It's happening against the URI update, so it's fota-server.motomotorcycles.com/update. Okay, so we're quite a bit closer. And then we see what looks like maybe a custom moto/1.0 user agent. Well, if we're going to pretend to be the app, then we better spoof that too, just so that we're being a little bit more stealthy, and maybe the app or the firmware update server won't respond to us unless it thinks we're really the app. So we'll spoof that as well. So this information, it gets passed into a retrofit call. Retrofit is a library that makes interacting with REST APIs from Java or Kotlin a lot easier. And the important components we need to locate in this call is the URL, which we already have. We've already got that. It looks like there's this authorization header, and we still need to figure out what that is. And then there's the user agent, which we've noted down previously. So here's the parameter for that authorization header. Let's see where it's coming from. So here's that function that it's pulling from. Oh, it's a static bearer token. So they actually did have another set of APIs that are doing things a lot more intelligently, but for the update process, they're just hard coding that key. So that's fantastic. So we've got everything we need. We've got all the parameters that we need to spoof a call to the update server as if we were the app, and we'll just use a curl command to do that. And what do we get back? We get a zip file. So let's extract this and see what we've got. So it looks like this zip file has multiple versions of the firmware, which is exactly what we've been looking for. But it gets even better. For reasons that are still unclear to us, they are shipping ARMLink dump files used to build this firmware. As you might be able to guess from the name, or maybe you already are familiar with the tool chain, ARMLink is a tool used to compile the object files, link it into the final firmware blob that gets put onto the device physically. What's great about this dump file is that it actually includes memory table information and symbols mapped to the function addresses in the final blob. And remember, I was talking earlier about if you're doing reverse engineering, it's a huge pain to figure out, infer a function's meaning by looking through the logic. So it was really nice of them to include this for us to reverse engineer it. So we're nearly ready to pull this into Ghidra for some serious static analysis. But first we need to figure out what the architecture is. And there are a huge number of ways to figure this out, but in the ARMLink files, there are references in the symbols to XMC 4500 and XMC 4800. Those are both automotive chips, that makes sense, and both of those are Cortex ARM systems. So that's all the information we need. We'll import one of these .bin files. We'll tell Ghidra that it's an ARM Cortex binary, and we'll use some of the information from the memory tables in the ARMLink files to set the correct base address. But we can do another step to make it even better. We'll write a quick Ghidra Jython script that imports those function names from the ARMLink dump file, and we'll actually label them in Ghidra so that after that we end up with some really nicely decompiled code that actually has the original function names. It's not perfect. We don't have variable symbols. We don't have comments, but it looks pretty nice.
So what was in the firmware? First thing we found, to do change this S, which we figured out later is the static salt of an authentication header that handles developer access to the firmware. So that's a good start. Digging deeper into the auth function, which is a challenge response flow, I found some instructions for how to generate the correct response for the challenge, and helpfully a note on who to talk to if you can't generate one. Mitchell immediately found this person on LinkedIn. It's not his actual picture, but it looks very similar. Looking more into the authentication for the challenge response flow to see if it was vulnerable. It's pretty simple. If you tell it to authenticate to one of the 4 privilege levels, it generates a challenge code. You type that challenge code into your authentication server that's running at that URL we just showed you, and it gives you back a response that you type in, and it authenticates you. But the whole process uses symmetric cryptography based on a simple salted hash of the challenge with the hard-coded salt that we just showed you. So you can trivially write your own challenge response generator. I am not really a C person, so that wasn't something I immediately wanted to jump into. So around this time, I was also poking around the unofficial service manual wiki. And like we said at the beginning, there's some screenshots of the mobile app saying that you can update the firmware via the app. So we decided to start looking into that as well because I like JADX more than I like C. So around this time, we had about 5 attack vectors potentially. Could patch the firmware, could try and hack the phone app, could try and spearfish Will specifically, could try and make a malicious app and get someone to download it, or we could try and hack the OTA firmware delivery server. The last 3 are outside the scope of the project. So we're left with the first 2, and of those, hacking the phone app is the easiest. So let's look at the app again. Opening it up in JADX, we see some activities in the manifest that seem to be handling the firmware updates. We can decompile those to see how they work. Now, blank slide for a moment while I get on soapbox. I am lazy by nature. And around this time, my manager had been getting on me to start using MCP tools. I don't like AI. AI is bad. But also, I don't want to spend like 10 hours reading Kotlin. So I installed the Ghidra, JADX, and Frida MCP servers and told Claude to look at them. And it made me stupider. But what did we find? Static firmware signing salt, which is hard-coded and the same across all bytes. The signature is the same, is just the SHA-512 hash of the firmware and the salt, and is stored in the metadata of the firmware file. So knowing the salt, we can sign our own arbitrary firmware. 2, absence of symmetric cryptography across the entire system. Discoverable salt rather than RSA extra signatures, which means we can forge any firmware or authentication response. 3, there's no root detection, and we can bypass any authentication of the firmware upload by doing a free-to hook of the app. 4, unauthenticated CAN bus flashing. If doing a free-to hook of the app is too hard for you, you can just plug directly into the CAN bus, which has no authentication whatsoever. And 5, hard-coded dev credentials. So putting this all together, there's at least 2 really easy exploit chains. Getting back on my soapbox, because I got woos before. AI is both bad for the environment and for your mental health, and is currently being used to generate CSAM on Twitter. You don't need to build the torment nexus, but I used it anyway, and so this has all been virtue signaling. Mostly, I just didn't want to uncritically endorse its use when you don't need it. Hurry up. OK. Secondly, vibe coding is not real coding. It makes you lazy, and I don't really respect people who vibe code. So here's some vibe code. This is a 1,200-line free-to hook that, when you open the app, it force navigates to the Bluetooth pairing activity. Then, using the app's own imported Bluetooth handling libraries, it scans for nearby Bluetooth-enabled motorcycles. It then spams BLE connection requests to all the motorcycles it found. And then finally, it makes sure that the custom firmware you gave it is signed correctly and uploads it via firmware update. The bike needs to be in pairing mode for this to work. but that takes all of 5 seconds, literally. And if it's never been paired with a different phone before, you don't actually even have to have it explicitly in pairing mode. Tool 2, CAN bus abuse. For about $100, you can build a tool with a Raspberry Pi Zero that connects to the bike's CAN bus, which goes directly into the battery management system, BMS, over the OBD2 port and uploads arbitrary firmware. Like I said, this is completely unauthenticated, and $100, well, like slightly annoying of a price, is less than 1/10 the price of buying a commercial harness to do the same thing. We'll get to what you can do with the CAN bus later. It's not great. I also made a controller script for this for the Raspberry Pi that I had. Do they work? Because we couldn't get a bike, we're not sure. But based on all of the reversing that we did, probably. So, what's the worst that could happen? Imagine you're a nefarious hacker, possibly with a motorcycle to sell, possibly with a Bluetooth connection and a test ride at the dealership. Unlike cutting brake lines or something, which is easy to spot and fix, maliciously reflashing the firmware is potentially invisible and can be done almost without touching the bike. If you add in a C2 server or a ransomware lockout, you can essentially control a $20,000 piece of equipment for free. So, I said control. You can't fully drive-by-wire, unfortunately. But what you can do is control the motor torque output, regenerative braking, battery discharge, cellular connection, and GPS tracking. So let's look at some worst-case scenarios. Torque control manipulation. If you apply maximum torque all at once, or apply zero torque at highway speeds. You can also force the bike to go into full reverse while at highway speeds, potentially throwing the rider. Oh, I forgot to click the button, so now it's going to do this for a while. Could also turn on full regenerative braking all at once, also causing a sudden decrease in speed. You can also, I forgot how slow these slides are. You can also tell the bike it's currently charging, which causes it to cut all motor power. None of these have lockouts for speed, so they work if the bike is in motion. You can also disable the safety controls that allow the bike to perform an emergency shutdown in the case of a battery fire or collision. And finally, you can send heartbeat messages with your GPS coordinates to an arbitrary receiver. And again, this isn't just like theoretical what-ifs. We actually scaffolded out some C++ pseudocode of what a C2 receiver Firmware would look like. So here's how it works. The bike has a built-in 4G LTE cellular modem, which it sends heartbeat functions to the app and to the Moto servers. We write malicious firmware update that hooks into the existing cellular communications module and MBB functions and bypass that normal heartbeat function to the Moto servers and instead send it to our controlled server. It then listens for received commands from the self-service and sends beacon packets back containing speed, GPS coordinates, timestamp, battery status, etc. And on command can do any of the vulnerable things that we just talked about, potentially leading to a crash or serious injury. We thought, well, maybe it fully uses up all the space on its chip and there's no even way to put in a C2 server. That's not the case. It turns out that they're not even close to using up the entire space on the chip. So inserting about 18 kilobytes of malicious code and a trampoline to get there is easy. We even found some code caves that you could put it in specifically. So back to Mitchell.
OK, so with a handful of serious vulnerabilities identified, we decided it was time to contact the manufacturer. At this point, it might not come as any surprise that there isn't a dedicated email for reporting security vulnerabilities. But there are a few general emails advertised on the official site for general inquiries, so I guess we'll try that. So we tried to reach out and get a better, we wanted to explain our situation, get a better point of contact, because we don't want to just be sending bunch of serious vulnerability reports just to whoever's handling these general inquiries. So we wanted an actual security point of contact. We got nothing. So we tried reaching out on one of the different email addresses that they had called out, and nothing. Okay, so I'll give them a call over their general support line. There's no way for them to ignore us now. So I got in contact with a customer service representative, and they passed me along to voicemail. So I left a voicemail explaining the situation, and I asked for them to call me back. Did they call me back?
Yeah.
Okay, so this feels like it might be intentional, but we persisted for 5 months sending them messages on LinkedIn and other email contacts. We even got, there were some salespeople who helped us out because they're better at trying to cold call people and get contact with them. Surprise, surprise, still haven't heard back from them yet. Okay, so what's next? Well, private disclosure didn't get us anywhere, but maybe now that we're doing a public talk, we can finally get that call back, work with the vendor to get these issues fixed, and we can eventually talk about them publicly with their real name, and continue doing even more research into this unusual hardware platform. So hopefully you all have learned a few new things in this talk about hardware hacking and firmware reverse engineering. Next time you have a really cool security research idea, you've got extremely limited resources, maybe you'll remember this talk because the manufacturer tried really, really hard to prevent any kind of reverse engineering. I don't think it was specifically targeted at us, but it feels that way. But you know, they refused to sell us main bike boards. Their boards were potted in the most annoying way possible, and they otherwise ignored all of our attempts to contact them. Despite all this, we still found significant vulnerabilities.
And just really quick, I want to say that for whatever reason, the asking for a VIN before getting equipment from them is like apparently general policy, because when I was writing this, I tried to get a copy of their like warranty to see how badly we'd violated the warranty by doing this hack. They will not give you one without a VIN number of a bike.
All right, well, I guess we'll pass it over to some Q&A.
Mind repeating the question for the recording audio?
Okay.
And I'll try and run this one.
Yeah, so the question was, did we consider hunting for a VIN on eBay or a sales record or anything like that? So something that we sort of skimmed over that if you read the bottom of the thing, we're going to do an unredacted blog post later. It will be more in depth than that, but something we sort of skimmed over is that to actually get the firmware downloads, it wants you to give it a hardware identification number and a VIN. What we found is that the VINs are validated on the server side based on probably a regex, because the format for the VIN is public on that service wiki that I showed. And if you just randomly generate one, it completely just passes through. So we didn't try that with the manufacturer just based on they might get really mad at us, but it probably would work there as well. So the question is, putting the bike into pairing mode, does that require pressing a button on the bike? Yes, it does. It requires the bike being parked, having its kickstand down, and pressing the mode button for 5 seconds, I think. Like I said, 5 seconds to put it into pairing mode, and it doesn't have a allow list of phones that it's paired with before. So even if it's paired with a phone before, you can still send it via a new phone. Did we consider spearfishing Will? Yes. But next question. Yeah. So the question is, can we submit CVEs even if we can't disclose the name of the manufacturer? Also, Mitchell, let me know if I'm taking too many of the questions. So we're currently working with the Carnegie Mellon CERT, CISA, I forget the exact acronym, but a coordinated disclosure organization that helps with responsible disclosure, because we figured that they might be more willing to work with like an official disclosure organ than with us personally. That's why we have a timestamp for early March, because that's when that disclosure window runs out, and they haven't responded yet. So probably can't get the CVEs without disclosing the name of the manufacturer, but we will try and do that once that timestamp for disclosure runs out.
Oh, I'll take a simple question. I'll take that. Yeah, the question is, what is a symbol? So symbols in this case are referring to, at least what we're talking about here is when the developer is writing a bunch of code, they're creating function names, they're creating classes, they're creating variables. Symbols are just the human readable, what we call the name of a variable, the name of a function, the name of a class, depending on how that code got compiled or how it's in its final form before it gets executed. That might just completely get stripped away. In the example of the ARM firmware, it should have been, or it was removed from the actual binary. There is no way to actually see within that what is the name of this variable, what is the name of this function, and that makes it extremely difficult normally to reverse engineer because we have no idea what this function does. We just have to read the logic, see the math that it's doing, and just kind of figure out and work our way through that. But because they included the symbols, now we can infer that, oh, this is called Moto update firmware, things like that. So that's what a symbol is. Does that answer your question?
Yes, thank you.
Yeah, so the question is, have we considered reaching out to a national organization because this is safety relevant? Yes, that's one of the things that the Carnegie Mellon disclosure people will help us do, theoretically. Where are the manufacturers located? They are located near Santa Cruz, California. Yeah, so the company recently went through a restructuring, as so many did, and moved their primary offices to the Netherlands, I believe. I think their main manufacturing facility is still in California. And I think Will is still in California, if I remember correctly. So the question was physical protections you can do on the bike. So the good news of this is that getting to the CAN bus is slightly annoying. The location varies by bike model, but generally you have to remove the seat or the side plating or something like that. So this is why we thought it was not necessarily feasible if you're just walking onto a shop floor. But if you've stolen a bike, if you're a manufacturer or a retailer or even just a mechanic, you could definitely do this. Probably an hour or so to get to the CAN bus. But yeah, there's best of class and also industry standard. There are actually some software level protections that you can put on the CAN bus to prevent stuff like this that, for example, disallow replay attacks, disallow unauthenticated access. None of those were in place here. And yeah, generally, your best bet is just going to be don't let someone access the CAN bus without your knowledge until they put any sort of protections in place.
The question is, did we try to attack the actual firmware update server itself? Is that right?
No, impersonate.
Impersonate the server. Yeah, so I guess if we wanted to impersonate the server itself, we would need to do some stuff that's pretty far outside of the scope of what we need to be able to, do some DNS cache poisoning in order to get traffic to come from, instead of going to the server to come to us. So yeah, that stuff all felt like it was a little bit too far outside of the scope of this pen test and what our employer would probably be comfortable with us doing.
I don't remember. Oh, wait, yes, they do. They do. They say that you can't hack the bike because the updates are all signed with the VIN number.
I think, what was it around the, they also had something around this manufacturer, they like to lock you out of hardware functionality on your own bike and then charge you to get it back. So they like to do subscriptions around, let's say, heated handlebar grips. Like, it's hardware, it's there, but they'll charge you a subscription to use it. So I think they've made a lot of security claims around the safety of that, which is kind of silly because, I don't know, that's very anti-consumer. The fact that they're actually using space on their website to say, oh, well, you can't break this because the subscription information is on the server and not the bike itself. Like, okay, well, that doesn't really protect the rider. It just protects your profits on your stuff that you're locking people out of.
So the thing that I wanted to do, which is going to lead into a vulnerability that we might work on for later, is I wanted to turn our C2 into a worm that could propagate over Bluetooth. But it turns out that one thing that this bike did fairly well is it distributed the control planes across different boards that are in different parts of the bike. And the boards only communicate over the OBD2 CAN bus. So the Bluetooth controller is separate from the cellular modem and is housed in the same board as the display. So we didn't have access to one of those. And if we were able to turn this into a self-propagating Bluetooth worm, we would need to have access to the Bluetooth control firmware to look at. So that is also why we didn't write any like hooks that do something flashy, like change the splash screen when it boots up or something like that. So exciting things that you can do for yourself. I think the easiest one that I can think of is you could disable the speed regulator because like with, which is also a safety hazard, obviously, but like with electric scooters, the top speed is actually mostly enforced by code rather than by mechanical issues. So you could just disable that and drive as fast as you wanted.
Yeah, so the question is so we talked about where they're just using static keys for the actual firmware update process, but there are another set of APIs that do more complex validation. So one of those things is what Persephone mentioned at the end of the talk around doing like regex to match the VIN. That was where we first seen that, was where making some requests against the API, pretending to be a bike with this arbitrary VIN. We don't know if the VIN really belongs to an actual motorcycle or not, probably unlikely. So that some of the components are using the actual VIN. That, of course, can be spoofed very easily. But then there are some other components that actually do require an account. I think around like the GPS mapping stuff, that does use an account. So that would be, but the correct way of doing this probably would have been to make our lives harder, would have been to have some kind of signing mechanism that only the bike is able to, there's some sort of key or some kind of value that passes through the phone into the bike, and the bike signs it somehow, sends it back up. And so the only way to actually retrieve the firmware is if you actually have an actual bike. That would have made our jobs a lot more difficult. So I think that probably would have been the right way to do it.
Is there anything is there anything that a user could do to patch their own bike to make it harder for someone like us to mess it up? Not without fully rewriting the firmware to the MBB, because that the phone app just serves the firmware updates, and then the MBB receives them. It checks that signing salts that we did, but theoretically, if you wanted to write several hundred lines of C yourself, you could write a custom firmware that uses a lot of the same functions, implements better signing, and then also has a like open source phone app to drop the firmware to it, or just always update over the CAN bus. That would suck, and I'm not going to do that. So
yeah, maybe hardware-wise, you can somehow remove the Bluetooth module. I don't know. You had that idea, right?
I had that idea. Yes, they're generally very expensive and like in the $200 to $400 range per like piece, and we don't really need them besides the like display module, which would be useful. Also, it's difficult to get them online without going through official retailers. They only show up on eBay occasionally, so that's sort of why we haven't done that.
Yeah, we also know that they do a lot of things to try to prevent you. Yeah, they try to do a lot of things to prevent you from doing maintenance on your own bike, and they will, like, the reason that you need, part of the reason you need to provide a VIN to the main bike board is so that it will communicate to the other components correctly. So I think we'd have a pretty hard time even just getting them to talk to each other.
Yeah, this is why there's an unofficial wiki on like replacing the manual, because they won't give you a manual for your own bike. So they don't do parts pairing. Were you interested in the MBB specifically or the BMS? I might have hallucinated that you said BMS because I was thinking about it, but did you have a specific part you were interested in? Okay. I mean, the things that I am most concerned about is people writing ransomware for your bike, because you could fairly easily just brick the bike. You could also, I've been like mentally referring to it as a Stuxnet for your bike, because by controlling the battery control boards, you can turn off the like safety limiters for charging speeds or open up the capacitors at full when they're not charged, which would essentially short the circuit. And this would sort of invisibly degrade your bike's power systems and potentially lead to like a battery fire while you're charging your bike. So that's what I was wanting to do with the worm idea. And it would definitely be much easier to make a botnet if you had a like functioning self-replicating worm, because then anytime you had like a bike go for a test ride on the manufacturer floor or something like that, you could just spread to multiple other nearby bikes. As it is, the C2 that we pseudocoded can control multiple bikes, but you'd have to individually install it on each one. Yes, it's a little bit unclear if you can send Bluetooth commands to that board from the firmware on the MBB, because it looks like most of the logic that we could find is just about downloading data over Bluetooth rather than sending commands out through the Bluetooth. But if it is possible to do that, then that would be the place to start. It's definitely, I think that even if you couldn't get something propagating from the MBB to the Bluetooth module, what you could probably do is get like one bike to be an attack vector that propagates to its nearby bikes from the Bluetooth module. And also definitely you could like change the splash screen, do things with the display panel. That looks like it's everyone, and we're about out of time. So thank you.
Thanks, everyone.